So, the stability was an important concept. The LaSalle theorem was an important concept, followed by we actually had things like construction of Lyapunov functions. They're important, there's no doubt, but they're not the most important concepts compared to, say, the fundamental theorems we just discussed. The only other thing that I would suggest for you to revise is linearization method, because it's a very powerful method. But then, as you have seen in last lecture and things like that, predatory prey problem, for example, concludes something, but it doesn't help conclude something else, and then basically we cannot throw nonlinearities just like that, right? When we throw, basically we end up with quite strange conclusions, right? So linearization is a good method in many cases, therefore it's important for us to know, but that's not always the best. Okay, so the next concept, we kind of went and basically started looking at we spent quite a bit in terms of understanding various topics, and then half of the class was understanding how to analyze these systems through Lyapunov functions and things like that, and eventually we started looking at robustness. When if we have an uncertain model, what do we do, and things like that. Okay, and but all the techniques that we have seen in robustness and things like that eventually are special cases of dissipative systems. So the key concept from the perspective of understanding the most important results in this particular course, the first one is of course Lyapunov function, followed by LaSalle's theorem. Then comes the notion of dissipative system, and then if you understand dissipativity, everything else becomes kind of trivial special case of that, right? And both these concepts put together probably takes you a long way in terms of understanding nonlinear systems. So anyway, let me remind, I won't go too many details and things like that. So we have this system with input and output. So this is a kind of generalization from the case where we don't have input. So dissipativity is that generalization, and it looks very similar if we didn't have this the integral part. Basically, essentially we are saying v dot is less than or equal to 0, which goes back to your standard Lyapunov condition, right? So when we have input, we instead we are saying basically it's going to be less than or equal to this integral of the supply rate, and we gave some energy kind of interpretation and things like that. If this satisfied is equality, then it's lossless, and something that's cute to understand, but not really. And then there is a slightly extended version called exponential dissipativity, knowing how the rate of some of these things are decreasing. Then that's quite useful in concluding asymptotic stability in some cases. Okay, so anyway, and if we have differentiable storage functions, then all these conditions can be expressed in terms of derivatives of this time derivatives of these storage functions on the trajectory, and therefore this will allow, see, these conditions are written in terms of on the trajectory, but if you get rid of those time dependence and then just treat them as algebraic condition, if those are satisfied, they become sufficient condition for showing dissipativity, right? So in fact that's quite a powerful observation everywhere in Lyapunov function theory as well as dissipativity theory. And then we looked at these special cases of dissipativity which were kind of discovered or invented long before the general dissipativity came. Willems, the originator of dissipativity theory, sort of combined all the notions of special cases of dissipativity and generalized and put it in the terms that we just saw, right? So as a special case of this dissipativity, we look at this passivity. Passivity is nothing but with specific supply rate of 2 u transpose y, and there are notions of strict passivity. There's input strict passivity, output strict passivity, input output strict passivity, and then finally something that's quite different but quite useful called non-expansivity, as you have seen in the last few lectures. Basically something called disturbance rejection is inherently connected to this non-expansivity, right? Small gain theorem and so many fundamental concepts are tied to this. But if we understand all these things, then basically all of those things become kind of special case. And then we have concluded that basically if we have these nice properties of passivity or non-expansivity, we can show that these systems, when there is no input, they are automatically stable. So, the original concepts were kind of developed around stable systems with inputs, and then basically natural to understand that basically, if you have a system and you are perturbing with some input, we want it to be stable when the input is not there. That's the basic criterion we would expect anyway. So these are just simple observations, but the key thing is basically, especially to connect to uncertain systems the way we did in robust stability analysis, dissipativity can be viewed even for static systems, whether they are nonlinear or linear. It doesn't matter. Linear, is simply some matrix operator. Matrices, in fact, linear algebra people actually view matrix as an operator rather than a quantity that we actually add, subtract, multiply, and things like that. Okay, and then similarly, nonlinear static systems, which is inherently connected to something called absolute stability problem that we have seen earlier, right? So anyway, so with that, basically we can talk about something called quadratic supply rate. It's a special case of the supply rate, which includes your passivity and non-expansivity and things like that. And then writing this v dot less than or equal to that quadratic supply rate. As we have done in the disturbance rejection case, we can bring everything into one side, and if that has to be satisfied for every input and basically less than or equal to 0, we can maximize that particular function over the inputs and basically take that maximum over u, and you'll get everything in terms of x in that particular case. If that x has to be less than or equal to 0, if the maximum happens to be less than or equal to 0, then the entire v dot is going to be less than or equal to that supply rate, and arrive at an inequality, right? And that inequality can be written in terms of a very nice set of 3 equalities in terms of these new functions L and W. And these are the celebrated extension to the famous Kalman-Yakubovich-Popov equations. In my experience, basically for linear systems, these can be solved as again inequalities. Even the nonlinear systems, though we state them as equality conditions, the best way to check them as actually nonlinear inequalities. And like I keep saying, basically they are very good in terms of if they are polynomial systems and things like that, we can use the SOS idea or the semi-definite programming method to look for these V's and Q's and R's and things like that, right? And then you can specialize to positive real lemma extension and bounded real. These are just a reminder that these are special cases. And then we will look at now a couple of solved problems, right? So I'm going to show that this particular system, the way we have, is lossless with respect to supply rate, and we will see in a second, remind ourselves, right? So how do we go about doing this? And with nothing to go on, we can always basically pick some thing like this, right? Half x square x dot plus alpha over 2 x dot square as your storage function. There are more general quadratic storage functions, but I'm going to attempt to use this and then see if I succeed, right? So this is a first good step when we not given, right? The more methodical way of doing this is actually basically throw away the notion of storage function and actually bring back this concept of available storage that I defined at some point, so over infimum and things like that. But that requires solving the solution and things like so differential equation, which is not easy in this particular case, this being nonlinear. So that becomes a very difficult thing. So instead, we attempt to check for different storage functions. So and then rest of it is standard by now. So I'm going to compute v dot, which is nothing but x alpha x dot multiplied by this in the state space formulation, you'll get x dot there, and then minus 2 plus x square x plus u. Okay, that becomes x dot minus alpha x dot times 2 plus x square plus alpha x dot u. Okay, it seems, you know, we can't really well, we can do the following. We'll get x dot times 1 minus 2 alpha minus 2 alpha 2 plus x square x dot plus alpha times y u, right? So, you know, unfortunately, I mean, I can choose my alpha to be such that this goes to 0, but then there is this particular part to it, and we don't know what to do with it, right? So, this doesn't seem to work, and then basically we may have to look for a different function. And what are the various possibilities? Well, and I'm going to leave that as a homework at this particular point. Basically, the most general quadratic equation one can think of is, you know, whole square plus gamma, and this gamma need not be there, but x dot square or something like that, right? This is the most general quadratic function. If this doesn't work, then we have to go for even, you know, more complicated stuff, and I would expect you to try this out, and then hopefully this works out. If it doesn't, then you'll have to go for integrals and things like that, right? So we will look at another problem, and then this problem is basically x dot plus x cube is equal to u and y equals x cube. And I will try a slightly different approach here. Instead of choosing quadratic, perhaps I'm going to choose x power p plus x squared q. This is one of the kind of guesses we did in the previous lecture on stability, right? So v dot is going to be basically going to be p times x power p minus 1 times x dot, okay, plus alpha q times x dot q minus 1 times minus x cube plus u, okay, and that's going to give me p times x power p minus 1 x dot minus alpha q x dot q minus 1 x cube plus alpha q x dot power q minus 1 u, okay. Y is x cube. Yeah, so you can clearly see that I can choose q to be equal to 2, and then p to be 4, and alpha to be 2, so that I'm going to get v dot is equal to simply 2 times q is 2, so 4 times x dot times u, right? So yeah, I think I made a mistake here. Actually, this is not x cube, but x dot itself, okay, and this is certainly passive, right? So this is passive with respect to 4 times yu, okay. So how do you ever end up showing non-expansivity? Well, in general, what will happen is v dot is equal to some 4u yu. You can actually show that this is less than equal to 2u square plus 2y square, but hopefully you have additional term here, and then that kind of subtracts this, and you will get something like 2u square minus a y square, showing that non-expansivity, right? So what here shows that basically if this system is non-expansive, and this choice of p and q and this storage function is not showing your non-expansivity, and you have to work harder to show non-expansivity using a different storage function, right? So, I mean, this is the drawback of just guessing the storage function. Instead, one can actually go back and do the available storage function, but then that requires solution. That's also difficult. So, we end up having to check for these things. The best thing to do is, again, use your KYP condition or the inequality, and then actually this is a polynomial system, and set it this as a semi-definite programming problem, and then numerically solve for your storage functions, and hopefully you can show non-expansivity in that particular case, right? So, it's not always easy to show storage functions exist and things like that, but so it's a matter of trial and error, and then we can show that these things to be dissipative and things like that, right? And once we show dissipativity, the advantage of having dissipative systems is basically when you have two systems in feedback with both dissipative, then we can show the overall closed loop is either Lyapunov stable or asymptotically stable, right? It's as simple as that. If you have two supply rates that satisfy this condition, R plus R sub C is less than or equal to 0 with the respective interconnections, right? In this particular case, I assume negative feedback, so U sub C is Y and U is minus YC. With that, and this particular condition is satisfied, then we have Lyapunov stability, and then we can guarantee asymptotic stability through multiple methods, either by assuming these are both exponentially dissipative, or sometimes we can actually use this zero state observability kind of a condition, along with one of them being exponentially stable and things like that. Sorry, exponentially dissipative, right? In the case of quadratic supply rate, the checking condition becomes much easier by looking at this matrix, and otherwise the observation is fairly straightforward. And the nice thing is basically when we specialize to feedback interconnection of passive systems or non-expansive systems, they are quite well behaved, right? And we actually, in the progress of the course, we looked at robust stability first, and then came and generalized to dissipativity. But in reality, if you understood dissipativity, we can look at robust stability as a special case, and that's what this slide is reminding you of. If delta satisfies a certain matrix inequality involving this quadratic expression, then basically that can be viewed as a static operator being dissipative, and we can look at this entire robustness problem as feedback interconnection of a system with some another static operator, in this particular case static system, and by ensuring the other part, without the delta part, is dissipative in a certain way, then the feedback interconnection is stable, and then that's essentially capturing almost all the results of robust stability, right? And by allowing these deltas to be actually dynamic operators, we can pretty much arrive at almost 99.9% of the results that are out there through dissipativity theory. And then the absolute stability problem that we discussed is a quite important problem. The technique of absolute stability is so powerful. Basically, it's essentially what it's trying to do is divide the nonlinear problem into a linear part and then nonlinear part, and the nonlinear part satisfies a certain dissipativity property or a sector condition in the balance of absolute stability. And by knowing just the linear part being a positive real or a positive dissipative with respect to a certain supply rate, we can guarantee that the feedback is stable, or the overall system is stable. And this is kind of presentation of absolute problem stability problem in terms of nonlinearities, but the power of absolute stability is actually dividing a nonlinear system into linear and nonlinear, and by identifying the nonlinearity belongs to some sector is actually quite powerful and keeps coming up. Recently we were trying to solve some problem involving some kind of underwater vehicles, and then it's a nonlinear system, and by rewriting it as absolute stability problem, we can actually solve that, right? So anyway, the feedback systems are quite useful in that sense. We can, if we somehow know that the plant is dissipated, just pick a class of systems that are dissipated with respect to a certain supply rate, and then we can stabilize this overall system, right? So anyway, let me quickly go through. If G1, G2 are passive, then the parallel interconnection is passive as well as negative feedback interconnection, right? So how do we what do we mean by this? First of all, Parallel interconnection simply means this, some kind of probably addition. Okay, so let's call this y1, y2, y1 plus y2, and the input is going to be same, right? So we know that G1 is passive with respect to y1 and u, G2 is passive with respect to y2 and u, and we want to show if y1 plus y2 with the input u, this parallel interconnection is passive. Well, it's actually as simple as what we see. So let's say the first one satisfies y1 dot is equal to u times y1. The second one satisfies u times y2. That implies v1 dot plus v2 dot less than or equal to u times y1 plus y2, right? Exactly what we need to show. It's a straightforward thing. But if we have a negative feedback interconnection, okay, let's say this is u, and there's a negative feedback there. So basically let's call this y, and this is y, and then this, let's say u1, this is u minus u1, right? So that's what we know is v1 dot, the storage function of g1 alone, is going to be less than or equal to its input u minus u1 times y. You may notice basically I don't necessarily 2 everywhere, because this we can always scale the v1 and then get rid of that 2. Similarly, v2 dot is less than or equal to its output, which is u1, and then input is y, right? When we these two, v1 dot plus v2 dot, I'm going to get is less than or equal to u times y, because the u1 y cancels. So the input of the negative feedback interconnection is going to be having output y, and then that is shown to be passive. So the negative feedback interconnection as well as parallel interconnection of two passive systems is going to remain passive, and I'm going to leave it as a homework. Suppose if we have two strict passive systems, maybe input strict passives, both of them are input stacked passive, can we say the same thing about the parallel interconnection and negative feedback interconnection? What if both are output stacked passive? What if one is input and one is output strict passive, right? And so I want that as a homework problem for you to consider, right? So a similar question, if both of them are non-expansive, what about the series connection, cascade interconnection? Can we say something about it, right? So what we have here is I have G1 here, and then that's cascaded. Perhaps I should have reversed, but it doesn't matter. Let's say U1, Y1 is equal to U2 and Y2, right? So I know that V1 is less than or equal to gamma 1 U1 square, you can put multivariable also, Y1 square, right? V2 dot is less than or equal to gamma 2 U2 square minus Y2 square, right? For the series interconnection, the Y2 is the output and the U1 is the input. So we need to kind of eliminate U2 and Y1. How do we do that? We need to be able to add these two. By simply multiplying the first equation by gamma 2, we can get basically V2 dot plus gamma 2 V1 dot is less than or equal to gamma 1 gamma 2 U1 square minus Y2 square, showing that the cascade interconnection is indeed non-expansive, but the gain is going to be multiplied by one another. Okay, so what this shows is if you have two systems in series connection and both of them happen to be such a way that this gamma 1 gamma 2 is less than 1, then we will end up with this so-called small gain theorem for cascade interconnections, right? So that brings us to an end of lecture 1 of this week 12, right? And we'll continue with this revision. Okay, the next class we will further look at